Okay, hi everyone. I hope that you're all staying as safe and healthy and sane as you possibly can in this difficult time. I hope that you guys are staying home, engaging in good social distancing, and hopefully we can all just get through this. I don't know about you guys, how you're spending the time in lockdown. Me personally, I'm just playing with my dog a lot. I'm doing puzzles and FaceTiming my parents. So I'm curious how you guys are doing. I miss seeing you all every day, and I really just hope that you're all doing as well as possible. So even though it's hard to retain a sense of normalcy in this crazy time, we're just going to keep chugging along with class, and we're going to keep learning, and we're going to keep trying to make this class as successful as possible for you. So that being said, today I'm going to talk about linear regression. Can you hear Jade? She's upset that I'm working right now. Jade, come here. Okay. Anyways, linear regression. This is a great topic to piggyback onto your Pearson's R correlation because in some ways linear regression essentially does some of the same things that a correlation coefficient does, um, in that it can help you assess the strength with which variables are related, but it's also a more useful and functional analysis in that you're able to do more with it than just a simple correlation coefficient. So I'm going to be doing the regression lecture in two installments. I'm going to start with your simple basic linear regression that really does kind of redux the same thing that your Pearson's R would do. And then in a second recording, I'll talk about multiple regression, which is where you can get a little bit more fancy with it. So in talking about regression, like I said, it's conceptually and numerically related to your correlational analysis. So your correlation, your Pearson's R that we learned how to do a couple weeks ago, this is a statistical analysis that's meant to help you assess and quantify a relationship between two variables. Once you know variables are related, you might want to use that information to generate predictions. Basically, if you know that there's a correlation between two variables, let's say your general GPA and your score in a particular exam, the idea is if someone was to give you their value on one of those variables, let's say tell you what they got on the SAT, the idea is within a certain measure of accuracy, you might be able to predict what their GPA is going to be. Not necessarily with perfect accuracy, but if the variables are related, you know you'll probably be somewhere in the ballpark. So how do you do that? You can't necessarily do that just with your Pearson's R, so you may want to piggyback your linear regression onto your correlational analysis because it helps advance your understanding and what you can do with your knowledge that variables are related. So what linear regression is going to allow you to do is make those sorts of predictions. So if you were to be given the value that an individual had on your first variable, if you know the variables are related, you'd be able to generate a prediction for their outcome variable, that second variable. Additionally, regression is going to have a function within this family of analyses that lets you quantify the accuracy of those predictions. So here's the basic approach. You generate your sample data, and what you do is you would create a scatter plot that depicts all of the data points within the sample data that you've collected. Then what conceptually and numerically happens is that that best fit line, that line that we've seen that gets superimposed through a scatter plot that sort of best sums up or summarizes the slant or slope of those data points. This line we've referred to as the best fit line, which is a great way to refer to it as because it, I think, makes sense in terms of how that line is created. It's the line that sort of, as best as possible, goes through the middle of the cloud of dots in your scatter plot. This line is also referred to as a regression line since it's the first step towards being able to do this regression analysis. The idea is once you have this best fit line generated, since you could extend the line further than the actual data actually existed in numerical space, the idea is the continuation of that line would help you generate novel predictions. So for any point along the x-axis, based on theoretically how that regression line would be, would land you on the x variable, and where it would land you on the y variable further up along the numerical axis than you would have been just within your sample data, you can use that to generate your prediction of x from y or y from x. So the basic approach is going to be gathering your sample data. Generally, the more the merrier. The more people that you include in the sample, the sort of better, more fleshed out of an idea of the relationship between your variables you'll be able to generate. But from the sample data, you generate that best fit or regression line, and the slope of that line is going to be what enables you to make those predictions anywhere in numerical space, even if the value you're given to generate a prediction off of wasn't actually contained in your sample data. The fact that that regression line is continuous would enable you to make any theoretical prediction. So some notation that we'll be using in this particular unit. Again, we're talking about the relationships between variables, so we're going to identify and distinguish our variables with our Roman lettering notation. So in this case, generally whatever variable we're conceptualizing as the one we're making predictions off of, or the predictor, we'll call that variable x. And whatever variable we're conceptualizing as our outcome, we'll call it y. Another name for this is the criterion variable. Typically, I call it the outcome variable, whatever it is we want to make predictions about. This y prime, y with this little apostrophe after it, is going to indicate that it is a predicted value that we're generating. Okay, so x and y are the general notations that distinguish the first versus the second variable. Y prime is the notation that indicates that we have generated a prediction for y. One thing I'll note is that defining your variables as x versus y, this is inherently arbitrary. You could switch which of your two variables is x and y, and it wouldn't actually fundamentally change your analysis that much. It would just change which variable you were conceptualizing as the outcome. Now, generally, it would be the case that your outcome is whatever variable you think happens second in time, like the example of the SAT being used to generate predictions about a GPA later in time. But that's not necessarily the only way that you can do things. You can switch up your notation, flip the x and y, and make something that happened in the past, your outcome, more like backtracking than making predictions. All of this is to say that in general, make y whatever variable it is you're trying to generate predictions about and call it your outcome. But at the end of the day, flipping what's x versus y, the notation is arbitrary. So then what you need to do in order to do this analysis is once the best fit line has been generated, you need to know the basic characteristics of that regression line. And if you remember anything about geometry, likely taking geometry in 7th or 8th grade, so a while ago, the two components of a straight line that help define and characterize everything that you need to know about a straight line. The first of these two components is going to be your y-intercept. So this is the y value at the point where your best fit or regression line crosses the y-axis. Okay, so if when x equals 0, what's your value of y? This orients your regression line along numerical space. You additionally need to know the slope or the slant of your best fit line. Okay, so essentially just the angle of that line, its steepness. Another way we define the slope is how much y changes across one unit of changes in x. Okay, so we've seen when we saw best fit lines in our correlational analysis that the slope of a line tells you things about the relationship between x and y. So if the line is slanted upwards, you would have a positive relationship versus sloping downwards. That would be a negative relationship. So the slope of your line can be positive or negative. And typically, a stronger slope or a steeper slope is often going to tell you that the relationship between your variables is stronger. Now, it's not quite the same as with your Pearson's R. There's no limited range within which your slope can exist, like how Pearson's R can only be between -1 and +1. Your slope for your best fit line is not sort of standardized in the same way that a Pearson's R is. So there's no inherent range that your slope exists within. It can really be anything, and it is grounded to the numerical scale of your variables. This is the basic equation that helps define a best fit line. I know likely when you took geometry, it was likely notated as y equals mx plus b, so your notation here is just a little bit different, right? Your y predicted value over here on the left is going to be generated by your knowledge of the slope, or beta, notated by the b. Whatever value of x it is you've been given, that's being used to generate the predictions, plus a, which in this case is the notation for your y-intercept. Okay, so this is going to be the basic notation that we use in statistics for defining a straight line. So it's got the same structure as y equals mx plus b, but the notation is just slightly different, but the way it's generated is the same. So if we want to be able to generate those predictions, we need to quantify those two components of your best fit or regression line. And here are the formulas to do that. Again, as with other formulas we've seen, the formula for slope might seem daunting at first, but again, it's nothing we haven't seen before. And in fact, a lot of this notation carries over from the computation of your Pearson's R. Regression is both conceptually and numerically related to correlation. So that's why a lot of the terms you see here are the same, right? That sum of xy, right? If you remember from your Pearson's R, the idea is if you see that sigma xy, you know that you're being directed to multiply for all individuals in your sample their x value by their y value, and then sum up all of those xy's after, okay? Sigma x, sigma y, that's just summing up all the scores x and summing up all the scores y respectively. So you know how to do that. And then sigma x squared, again, it's the prioritization of different operations. So sigma x squared, you know that you need to square all of the x values first for every single individual in your sample and then sum them up. So nothing here is foreign or novel to you. The idea is if you just stop and you look at the equation, this gives you a roadmap for how you would complete that computation. And in fact, a lot of it should feel quite similar to how you computed your Pearson's R. For your y-intercept, this one's pretty simple. You need to do this one second because part of computing your y-intercept is going to rely on your slope. Then from there, you just need the mean of y and the mean of x, right? That y bar and that x bar, that's the mean of y and the mean of x, and you need those things to generate your y-intercept. And once you have that, you can have your completed regression equation that would help you generate novel predictions. So I'm going to show you an example of how this work would go. Let's say I'm interested in the relationship between time spent studying and final grade in neuroscience class, and the data is collected from 15 students. Your data would look something like this, right? It's the same thing with your Pearson's R in that it's all about pairs of scores. So for each individual in your sample, you need to know their value of x and their value of y, because the idea is we want people's values of x and y to be co-varied with each other. So the idea of variables being related is that if you know their amount of time studying, if those variables are related, the idea is you could, with some measure of accuracy, be able to predict their grade. If your variables are unrelated, if the Pearson's R is weak or non-significant, this process is probably not even really worth your time. But the idea is if the variables are correlated, then going through this process of generating your regression line would be worth your time because you know your predictions are going to contain some measure of accuracy. Okay, but here's how you would approach the work of creating that regression equation. Right, so first you could visualize your data as a scatter plot. You could compute your Pearson's R as a preliminary analysis to see whether or not there's a relationship whatsoever. Okay, but as you could see from the scatter plot, those data points appear to be telling the story that these variables are pretty strongly related and in a positive direction. The ways you can visually assess these sorts of characteristics of the correlation from a scatter plot, right, you can see that the dots form a pretty coherent linear shape, and they appear to be clustered pretty close to any superimposed best fit line that we would create. So this is telling the story that those two variables of study time and grade are co-varying together to a pretty strong degree. Additionally, you can see based on the fact that that trend of the data points is sloping upward, that there appears to be a positive relationship between those variables as well. So the idea is that there's a best fit line associated with that scatter plot, with that cloud of data points. So in order to generate that best fit line, we need to create the equation, or we need to create the terms that would allow us to compute first the slope. So to do this, you would create a table very similar to what you did when you computed your Pearson's R. You just don't need a y-squared column. You don't need that one here. But you do need to create a table for yourself where you can get the xy term and the x squared term. And overall, you need your sum of x, sum of y, sum of xy, and sum of x squared. Proceed with the work. Again, most of the effort is done in this step, and the minutia of just going through these basic arithmetic functions over and over and trying to pace yourself to minimize your nitpicky little mistakes. But overall, this is nothing we haven't seen or done before. So then you generate those terms that you need. And again, once you have your sum of x, sum of y, sum of xy, and sum of x squared, you have the 4 terms you need to go turn around and compute your slope. So you've got your formula for your b value, call it a beta value or a slope, and you just solve for b. Okay? Again, I'll reiterate that as opposed to a Pearson's R, your slope can be any value. As opposed to a Pearson's R, in which the equation has a numerical mechanism within the formula that creates that standardization, the same can't be said for this particular approach for regression. So ways that you can check yourself, if in the scatter plot you do see that the slope of the dots is upward, it should be the case that the slope you compute has a positive value. If you do see those dots sloping downward, on the other hand, your slope should be of a negative value. Beyond that, there's no strict way to make sure that numerically you're in the right spot, but you can tell that your direction is going the right way. So once you have your slope, you can solve for your y-intercept, notated with our a. To do that, you just need to first get the mean of your variable y and of your variable x, nothing you haven't seen before. And then from there, since you already have your slope, it's pretty easy to compute that y-intercept for yourself. Again, the y-intercept is not restricted to any specific numerical range. You would be able to tell sort of roughly by visualizing your scatter plot and drawing your best fit line whereabouts in numerical space the y-intercept reasonably could be. But again, you can't with perfect accuracy be able to tell a specific range numerically that your y-intercept should be in. But you can get a sort of a rough ballpark by just looking at your scatter plot and creating that best fit line for yourself. So then this is your full-fledged regression equation that defines the best fit line for that particular sample of data. I will recommend that in linear regression, generally, please round to 3 decimal places. The reason is if we're trying to make predictions, the idea is we want that slight extra measure of accuracy that comes from having more decimal places included. So the idea now is that this equation would allow us to generate y predicted scores given that we know someone's value of x. Basically, once we know someone's value of x, we just solve for y predicted, and that's the prediction. So let's say we have an individual who tells us that he studied 105 minutes and asks us to generate a prediction for his final grade. The idea is we're getting the value for x and we just need to solve for y predicted. Pretty simple. Buddy's y predicted score would be 76.45. So that would be our basic prediction. If we were asked to generate a prediction on the basis of that regression equation, this would be where we would expect Buddy to fall. That's not quite good enough though. What we want to do is we want to check additionally the accuracy of our prediction. So how do we do that? Well, we have a series of people from our samples and we can use their values to generate their predicted values against their actual values, right? So the idea is we can check the accuracy of our prediction by using a score and outcome that we already know. So for example, student number 6 studied for 85 minutes a week. What would her expected grade be? Well, we would just do the same thing, take her x value and solve for y predicted. Her predicted outcome would be 70.70. Now here's the problem. Like I said, we're evaluating against a score we already know. Student 6 did not, in fact, get 70.70. She actually got 80. So clearly we're a bit off the mark here. Now, is this going to render our regression equation useless? No, absolutely not. Unless you have a perfect correlation, i.e. a correlation of +1 or -1, you are inherently going to have some error in your prediction. Only if you have a perfect correlation, a perfect one-to-one relationship between your variables, there will necessarily be some error in your estimate. So this prediction error, right, we're generally going to have some there. As I've mentioned before, we're not necessarily expecting variables to be perfectly related. That doesn't really happen in real life altogether, that often. So prediction error is fine. We just want to be able to quantify it. The way we do that is with a outcome that we refer to as the standard error of the estimate, or SEE. This is going to look a little bit like your standard deviation for the mean. The key difference, though, is as opposed to standard deviation, you are just evaluating the distance of all of your scores from a single numerical point, i.e. the mean. Standard error of the estimate is meant to quantify the distance of your data points from where you would predict them to be based on your best fit line. But the idea is we don't necessarily predict all of our values to be the same exact numerical outcome. We necessarily are expecting their outcomes to differ depending on where they fall along their first variable. So we're going to need to have some extra steps before we evaluate that distance from where the scores are to where we would predict they would be, because unlike standard deviation, it's not a single numerical point. So you can think of standard error of the estimate as much like a deviation measure. So as opposed to standard deviation, whereby we're taking raw scores and evaluating their distance from a single number, the mean of that series of scores, standard error of the estimate is instead going to be the quantification of the deviation of your actual y-scores from where they would be predicted to fall based on the regression line. So essentially, the distance of y from y predicted. This is going to quantify the distance of your actual y-scores from that best fit line. Again, recall, only a perfect Pearson's R has data points that all fall along the best fit line. If you have anything that is imperfect or at all less of a magnitude than a -1 or a +1, you are necessarily going to have some distance between your data points and that regression line. Again, that's okay. It's just that in computing the standard error of the estimate, we're going to quantify just how much error there is. So again, regression is both conceptually and numerically related to a correlation. And in the standard error of the estimate, we can also see that it's conceptually and numerically quite related to the formula for standard deviation. So recall our formula for the standard deviation of the mean. Right, it's about taking the deviations of all our scores, x minus x bar, squaring all the deviations, right, since to sum up all the deviations would lead us to a score of 0. We square all the deviations, then sum, then divide by the degrees of freedom, then square root. This is your formula for standard error of the estimate. So see that the structure of the equation is quite similar. It's just the deviation score, quote, quote, deviation score, is not x minus x bar, it's y minus y predicted. Okay? From there, the structure is quite similar. You take the difference of all of the y scores from their y predicted score. You need to square them because the same problem occurs in standard error of the estimate as with standard deviation, whereby if you were to sum up all of the deviations of y minus y predicted, they would inherently add up to 0. Okay? Since the best fit line necessarily is slapped right through the middle of that cloud of dots, some of your data points naturally will be higher than their predicted value, and some will inherently be lower. There's numerical balance above and below the regression line. For that reason, if you were to just add up all of the y minus y predicted values, they would, just like in standard deviation, add up to 0. That's why the formula looks the same. You're going to do y minus y predicted for all of your data points, all the individuals in your sample, square all of those values, then sum up all of those squared differences, divide by degrees of freedom. In this case, degrees of freedom for standard error of the estimate is n minus 2. The 2 standing for the 2 variables currently being contemplated in this analysis. And then same, you take the square root value and you're done. Okay, so this is what your approach to the work would look like. Okay, the equation looks the same to standard deviation, but there's this extra step we have to do because, as I mentioned, you're not trying to get the distance of a score from a single numerical point. You need the distance of your y-score from y predicted. But the y predicted score is going to be different for all 15 of these individuals. So you actually need to go through, in this case to all 15 of your individuals in the sample, and generate their unique y predicted score. To do this, you use the regression equation that you've created, and you just go down the line, taking all 1 through 15 of the students, plugging in their x value into the regression equation, and solving for y predicted. Okay? So these are all my y predicted values for all 15 of my individuals. As you can see, there's distance from all of those y values in that column from their y to their y predicted, right? Our predictions are just a little bit off. Again, that's okay. That's because the data points are not all perfectly falling along that best fit regression line. Also, you'll notice that some of the y predicted values are higher than you would have predicted, whereas some are lower. So when you go through and you create y minus y predicted, some of those values are positive, some of them are negative. Again, this is by virtue of the fact that some of your predicted scores will inherently be higher than people got, and some will be lower than what people actually got. Okay, again, some of the data points, based on the fact that the best fit line goes through the middle of the cloud of dots, will be higher than expected based on the line, and some will be lower. So if you were to add up all the values in that y minus y prime column, it would add up to 0. Now, if you do this on your own, you might find that it ends up being 0.002. When you add up that entire column, that's likely perfectly fine, right? We're having to do a little bit of rounding here. So if it is the case that you're basically at 0 within a certain margin of error, likely that's fine. But as with standard deviation, it's a good idea to add up all of the values in that y minus y prime column and make sure that they add up to 0. Because if they don't, you may have computed one of your y primes incorrectly. Again, since the same problem would present itself if we were to just add up that y minus y predicted column of the values in that column adding up to 0, that's why the next step is to square all of those y minus y prime scores. Again, this gets rid of the problem of some of the scores being positive and some of them being negative. Okay? So then this value, as with the sum of squares from your standard deviation, is what we actually use to compute our standard error of the estimate. So then from there, the hard part's done. The formula from here on out is pretty easy. Okay? Again, you take that whatever sum of squares-y value is for the standard error of the estimate, the squared residuals, I'm not sure if there's a legit term for it, that goes into the equation over the degrees of freedom, square root, bam, you're done. There's your standard error of the estimate. So the standard error of the estimate gives you an indication about how much on average your data points were away from that best fit line. So, as opposed to your Pearson's R in your regular correlational analysis, where the Pearson's R represents a quantification of strength, in regression, it's our standard error of the estimate that quantifies the strength of our relationship. As your correlations get stronger, you have better predictive accuracy. Better predictive accuracy, smaller standard error of the estimate. So the standard error of the estimate provides a quantified version of the confidence that your predictions are accurate, right? The closer to zero your standard error of the estimate is, the more strongly accurate your predictions will be, and the more strongly related your variables are. So again, I'll reiterate that both correlation and linear regression at some points accomplish the same thing. They are both conceptually and numerically related, your regression analysis and your correlation analysis. They both, in their most primary versions, do the same thing. Again, regression is going to get more complicated once we get to multiple regression, but in its most basic form, linear regression and correlation are analyses to help you assess the strength with which your variables are related. So numerically, the Pearson's R, I've mentioned before that the Pearson's R equation, it does this standardization process, right? Again, the range of a Pearson's R can only be in between -1 and +1. That's actually because what the Pearson's R formula does is it actually gives you the slope of the regression line should the scores be standardized and replotted as z-scores, right? So we've mentioned before when we talked about z-scores that this is a way to standardize your scores such that any variables that are on very different numerical scales can be compared to one another. Pearson's R naturally accomplishes that. So that's what actually the Pearson's R is. It actually does use a sort of a version of regression that pre-standardizes your variables for you without your even needing to do much work. It just happens naturally along the course of computing your R. So there's a natural relationship numerically between linear regression and correlation using a Pearson's R. There's a numerical trade-off between your Pearson's R and your standard error of the estimate because these are the two numerical outcomes in regression and correlation respectively that give you a measure, a quantified measure of the strength with which your variables are related. So there's actually an inverse relationship between your Pearson's R and your standard error of the estimate. The stronger your R value, so the closer to +1 or -1, the closer your standard error of the estimate gets to 0. Okay, so a perfect correlation would be represented as both a perfect Pearson's R of +1 or -1. In these two graphics, you would see it would be a +1 since both of these visuals depict positive correlations. Okay, and since all of those dots fall onto that best fit line, additionally, there is no error in the estimate. So when there is a perfect relationship between variables, that would be a case in which you see Pearson's R being as high as possible and standard error of the estimate being as low as possible. On the other hand, when there is no relationship between variables, if there was to be a zero correlation representing no covariance between variables x and y, okay, in that case, in terms of predictive accuracy of variable y, you wouldn't be able to use any of your information about variable x to generate predictions about variable y. The only way numerically you could create a prediction for your y score is just going to be information from the y variable itself, so really just the mean of y. So in fact, what ends up happening when you're dealing with variables that are completely unrelated, it is only the deviation of the y scores from the mean or the standard deviation of y that has anything to do or tells you anything about the standard error of the estimate. Okay, this point is a little bit confusing. It's highly conceptual, but think about it this way. There would be one case in which you would have perfect predictive accuracy or no error in predicting y scores, despite there being no relationship between x and y. It would be if there was no deviation within the y scores at all. That is to say, all of your y scores were the same. Okay? every individual in your sample had the exact same value of y. That would be a case in which the standard deviation of y was 0, and there would be no error in the estimate of predicting y from your actual y scores. I wish I could draw it on the whiteboard for you. I know this is a tricky point. But basically what this means is that if you're dealing with completely unrelated variables, the only way to determine error in making predictions about y is going to be on the basis of any variance or standard deviation within the y variable itself. So if there's no relationship between x and y, the only information you have to go on in making predictions about y and how accurate your predictions of y are is going to be the information pertaining to the y variable itself, the mean and standard deviation of y itself. Okay, so I've mentioned this term before when we talked about correlation. It is going to become more useful for particularly when we get to multiple regression in the next recording. But I've mentioned this r squared, or coefficient of determination, before. This is going to be a outcome that tells you about the proportion or percentage of variance shared between your variables. So this is another outcome that can be considered a quantification of the strength with which your variables are related. Okay, so again, as I just mentioned, the strength of or accuracy of your predictions of y when the variables are related is going to hinge on the standard error of the estimate. The strength or the accuracy of your predictions of y when the variables are unrelated is going to be the standard deviation of y. So basically, if you know both the standard error of the estimate and the standard deviation of y, basically you could use all that information to determine the amount of covariance shared between variables x and y. Basically, by partitioning out any error in the relationship between x and y, the standard error of the estimate, while taking into account the natural amount of error or deviation within y itself, or the standard deviation of y, basically you see that the coefficient of determination, or your r squared, is additionally both conceptually and numerically related to your regression analysis. Okay, so r squared is going to be a value that tells you about the percentage of variance shared between your variables, right? There is only 100% of variance to explain. So as you can see, you can basically figure out the proportion of variance shared between your variables by starting with the 100% of variance to explain, that 1 stands in for, and then partitioning out any error in the model, standard error of the estimate, as well as the error associated with y itself, or the standard deviation of y. So basically, this is mostly to reiterate that there is both conceptual and numerical relationship between regression and your Pearson's R correlation coefficient. So again, you see an inverse relationship. The smaller standard error of the estimate gets, or closer to 0, the closer that coefficient of determination gets to 1, or 100% of variance covarying between your variables. Okay, so to show you an example of how you could use this from this example that I just used to figure out the proportion of variance shared between your variables. Again, to do this, you would need your standard error of the estimate that we've already computed. You would need your standard deviation of y. And then from there, you can use that information to partial out any error and leave yourself with your coefficient of determination that tells you the percentage of variance shared between your variables. Again, basically you can go back and forth between the numerical outputs associated with correlation and regression, and they're all going to give you different ways of communicating the same information, i.e. information about the strength with which your variables are related. So I'll just show you real quick how you could do this analysis in SPSS to check your work. Similar with correlation, we just need to have a line in SPSS devoted to each one of our participants and have their score of X and their score of Y. Okay, you can run an initial Pearson's R just to make sure that the variables are related whatsoever, because if they're not related, then doing a regression is probably not very much worth your time. One thing I'll reiterate here, just because I know it's easy to forget, that Pearson's R, that p-value in that sig row of 0.000, remember that there's no such thing as a p-value of 0. That is just SPSS indicating that the correlation, the p-value, is significant at less than 0.001. It only goes to 3 decimal places, but always remember there's no such thing as a p-value of 0. It's impossible to have a 0% chance of making an error. So whenever you see that 0.000 in SPSS, you should write up your p-value as less than 0.001. Just letting you know. All right, so then from there, how do you do your regression analysis? So go to your same Analyze drop-down menu, go to Regression. There's lots of different kinds of regression. It's a very useful analysis. There's different ways that this analysis can be used. Linear regression is just the particular kind that's used when we're talking about data that is related in a linear fashion. As we mentioned with correlation, if your variables are related in a more advanced, let's say curvilinear way, there would need to be a different analysis used, but here we're going to assume that our variables are related in a linear fashion, thus we choose linear regression. Then in this spot, you're going to want to put whatever variable you're conceptualizing as the outcome into that dependent box. So you just click in the list of variables over on the left on whichever one you're conceptualizing as your outcome, and you click it over using that arrow into the dependent box. Again, dependent variable typically refers to our outcome. We're not doing a causal-based experiment here. And again, which variable is being conceptualized as X versus Y, you can flip these around all you want. It's not going to do that much to change your interpretation, but whichever variable you're thinking of as the outcome, go ahead and throw that in the dependent box. Then whichever variable you're using to generate your predictions, your X variable, click that and move it over to the right into the independence box. You shouldn't need to do anything else here, just click OK. And then this is your output. There's a lot here, but there's only a couple things you actually need to pay attention to. The first is going to be this model summary bit of the analysis, where, as you can see, you've got your Pearson's R. It's the same as the Pearson's R from the correlational analysis. You've got your R squared value. Adjusted R squared is typically going to just be a slightly diminished estimate of your coefficient of determination. As we'll get into later, if you have multiple regression, you have more than just 2 variables currently being contemplated in the analysis. The adjusted R-square corrects for the number of variables included in the model. You can use either one. I guess I'd err on the side of saying you should use the adjusted R-squared, but they're typically not going to be super different. And then your standard error of the estimate. So these are all the values that tell you about the strength with which your variables are related. Again, your Pearson's R, your coefficient of determination, and your standard error of the estimate. Those are all different ways of quantifying the strength of the relationship between your variables, just from slightly different approaches. At the bottom, in the coefficients part of the output, that's where you see all of the components of your best fit regression line. So the places you're going to want to look at to get those components for your best fit line. Okay, your slope is going to be here. It's going to be to the left of the output under this unstandardized coefficients and under that B column. Okay, now specifically when you're trying to get the slope, make sure that you're looking in the row in which you see the predictor variable listed. So minutes was our predictor variable, the X value that we were using to generate predictions. The value in the B column in that row is going to be your slope. Now, as we're going to get into later, you can have multiple, you can have more than 2 predictor variables, you can have as many as you want. Okay, so in order to make sure that you've got the correct slope, just make sure that you're looking in the row that has the predictor variable you're currently thinking about listed in that row, and then go over to the B column. This value, though, there's always going to be a single value in this column at the top in the row that's labeled constant. That's your y-intercept. Okay? No matter how many variables you have in your regression, there's going to be a single y-intercept, and it's going to be that value listed in that constant row. You additionally have a p-value here. Assessing your regression for significance, again, is not going to really add any understanding beyond just assessing your Pearson's R for significance. In fact, if you're just doing a regression with one X and one Y, or two variables, it's the same as doing a bivariate correlation in terms of evaluating for significance. So that p-value is going to be the same as from your Pearson's R. So again, p is just less than 0.001. Okay, so I'm going to stop this recording now so that you can take a little bit of a break. And then I'll come back and we can do multiple regression and also try out a practice problem.